Part D. Use a graphing utility to graph d equals d of x. So recall our function from above is d of x equals the square root of x to the fourth minus 13x squared plus 49. So I'm going to enter y equals square root of x to the fourth minus 13x squared plus 49 into the graphing calculator. So here I've got the function entered into the y equals editor. Now anytime we enter an equation into our calculator to graph, we want to think about a reasonable viewing window. That's reasonable values for the x and y axes to display. So in this case, since we're talking about distance, d represents distance, we know we only need positive y values. So we need our y values to start at 0. So if we look at our window, a typical default for our x and y values really is negative 10 to 10. So it's reasonable for the x values to leave negative 10 to 10. But like we just said, since d represents distance, we know our y values are only going to be positive. So I'm starting my y min here at 0. So I'll go to my graph, and I get this shape, kind of a W-looking shape. It looks like it has symmetry with respect to the y-axis. So I'll make a little sketch of this in my notes here, and I want you guys to do that too, so you have it to refer to. So just make an approximate sketch of that shape. Okay, so we'll go back to our graph here for part E. Part E asks for what values of x is d smallest. So smallest should clue us into the minimum value of the function. So we'll use our calculate feature here on the graphing calculator to calculate, and we can look at this graph and we can see two little dips in the graph. So when you have these two little dips, those are local minima, and those will be values of x for which this function d is smallest. So I'll hit second trace to calculate. I want option 3, minimum. And now I have got to enter a left and right boundary. So I'm already closest to my right minimum here. So I'll just arrow just a little bit left of that little dip in the graph and hit enter. That's entering the left boundary, putting the arrow up here. Then I'll arrow over just a little bit to the right. Or we can also type in an x value if we want to move faster than that. Hit enter. It marks these two arrows, so I can see I'm going to have a minimum right between here. So you can make a guess, enter a guess, or just move your cursor close to that little dip and hit enter. And I can see that my y value here will be smallest when the x value is about 2.54, etc. So we'll just round this to about 2.5. As always, pay attention in my math lab for how they'd like you to round your answer. So if I go back to my problem here, I know it'll be for x equal to 2.5. That's one of my minima, one of the x values of my minima. So now we'll calculate the other one. Now it certainly looks like there's symmetry here. So it would make sense that if this is a positive 2.5, this is probably negative 2.5, but we want to verify for sure. So we'll second trace to calculate. Again, we want the minimum, option 3. So now we can arrow all the way over. On my tablet here, there's quite a delay, so I'm just going to enter an x value. So I know I'm counting by ones on the x-axis here. I go from negative 10 to 10. So I'm going to ballpark this point here, especially if we know that this is positive 2.5. Just something less than negative 2.5, so maybe like a negative 4 I'll type for my left boundary, just for instance. And so it marks my arrow. And now for my right boundary, again, I can cursor over, or to go a little faster, you can always type in an x value. So I'll hit enter. This marks another arrow. So now I can see I'm going to have my dip in the graph here, this minimum, in between these arrows. So I can cursor close to that dip, hit enter. And I can see, again, I've got my minimum value of 2.598, etc., at the x value of negative 2.54, etc. So there is that symmetry that we observed. So we have a minimum at x equals positive 2.5 and negative 2.5. So those are the x values for which the function d is smallest. And we can go over and mark on our graph here, these 2 points were approximately 2.5, 2.6, and this was approximately negative 2.5, 2.6.